Welcome to this week's third and the last lecture. In the last lecture, we have seen the structure of the null spaces, and based on those structures, we have learned, or the dimensions of those structured subspaces, we have learned how to extract information about the Jordan canonical form of a matrix. So remember, we calculate the dimensions of these null space of A minus lambda I to some powers, and then based on those dimensions, we extract the Jordan canonical form of a matrix. Let us remember what we did so far. So we have seen the following facts here. If A is in Cn by n, then we are going to have the characteristic polynomial d of s in the following form: I from 1 to k, s minus lambda I to the power ri. Okay? And similarly, the minimal polynomial m of s is the product I from 1 to k, then I would have s minus lambda I to the power mi. And we have seen that the powers in the characteristic polynomial, they should sum to n. I from 1 to k, and I would have here ri, this should sum to n. And furthermore, the minimal polynomial powers should be between 1 and ri. All right? These are coming from the properties of the minimal polynomial. And then we have seen our decomposition. So Cn can be decomposed into these null spaces. But maybe before the decomposition, I can just now first define the matrix sigma I. If I define the matrix sigma I as A minus lambda I identity, then I can use this shortened notation for the matrix A minus lambda I identity. In that case, I would have this decomposition Cn is null space of sigma 1 to the power m1, null space of sigma 2 to the power m2, going until null space of sigma k to the power mk. Okay, we have this type of decomposition, and furthermore, we have the dimensions of these spaces. Dimension of the first null space here is R1, dimension of the second one is R2, and dimension of the last one is RK. So that when I sum these dimensions, I obtain the dimension of the overall space, which is Cn. This is the property of a direct sum decomposition. And then we have seen the structure of these null spaces. So structures were like this: sigma I to the power 1. This is my eigenspace, smallest null space. And I would have null space of sigma I square. And these continue until null space of sigma I to the mi minus 1. And I have one more null space of sigma mi. This is the largest null space that I can get, and the dimension of it is ri. All right? And I know that because these are the proper subset notations, dimensions of all of the smaller subspaces would be strictly smaller. And I know that dimension of the eigenspace should be at least 1. Okay? Because every eigenvalue should have at least one eigenvector. That means that dimension of the eigenspace should be always larger than or equal to 1. Okay? There is at least one linearly independent eigenvector for each eigenvalue. That is why we have the property greater than or equal to 1 for the dimension of the eigenspace. And then by looking at these dimensions and what happens when I continue here? I know that there would be equality if I try to increase the powers here. So the dimensions will be equal and the null spaces will be equal forever. And by looking at the dimensions of this sequence of null spaces, we learned how to find actually the Jordan canonical form corresponding to a single matrix. So what was the result? So I have dimension of null space of sigma I to the power L minus dimension of null space of sigma I to the power L minus 1. These differences would define the number of Jordan blocks. And this is equal to number of Jordan blocks with size larger than or equal to L for lambda I. Okay? This is one of the facts that we have learned. And finally, we have the minimal polynomial power is the size of the largest Jordan block for lambda I. Okay? And what about the number of eigenvectors for an eigenvalue? It is the dimension of the null eigenspace here. Dimension of the eigenspace gives us the maximum number of linearly independent eigenvectors corresponding to an eigenvalue. Okay? So these were the facts that we have seen so far. And we have solved one example on finding the Jordan canonical form from the matrix A by calculating these dimensions of these null spaces. And now we're going to solve two more examples on the same topic. So when we know the dimensions of these null spaces, we don't even have to know the matrix A. So if we are given these dimensions, we can find its Jordan canonical form without knowing the actual values of the elements of A. So these two examples will illustrate that fact. So I have example. So suppose a matrix A, which is in C8 by 8. So this can be also real valued, it really doesn't matter, has the following subspace dimensions. So let us say that dimension of null space of A minus 3 identity, this is the eigenspace, it is 5, and dimension of null space of A minus 3 identity square, this is given as 7, and finally dimension of null space of A minus 3 identity cube is given as 8. And from these values, we need to extract some information about this matrix. What is its characteristic polynomial? What is its minimal polynomial? And what is its Jordan canonical form? Okay? So we are asking the following questions. D of S is a question mark. M of S is a question mark. And what is the Jordan canonical form corresponding to such a matrix? Okay? So now I would like to start solving this question by noting to you that this dimension is 8. And matrix A is an 8 by 8 matrix. So what happens when so the matrix A is from C8 into C8. Okay? And these null spaces are all elements of the domain. Domain and codomain are the same, so I can talk about these null spaces are subsets of the domain and the codomain at the same time. Okay? So we see here that this null space is a subset of domain, and null space of A minus 3 identity square is a larger set because its dimension is strictly larger than 5 here. And dimension of null space of A minus 3 identity cube, its dimension is 8. Okay? So therefore this null space is a subset of this domain, and so here I can write A minus 3 identity to the power L here. This null space is a subset. Let me put a subset here. Is a subset of C8, and furthermore its dimension is 8. Okay? I have a subspace whose dimension is 8 of the overall space C8. Then what can you say about this null space? This null space has to be C8 itself, because if you have a subset or a subspace of a space which has the equal dimension as the space itself, that should be equal to the space itself. Okay? So I have here null space of A minus 3 identity to the power 3 is equal to C8. Okay? Because its dimension is 8 and the overall space dimension is 8 here. So I can write here the same fact as the following. C8 is equal to null space of A minus 3 identity to the power 3. So this is my decomposition for this matrix. Remember, we have this type of decomposition for multiple eigenvalues, multiple distinct eigenvalues. And in this case, since I have this type of decomposition for this matrix, I see that I have only a single eigenvalue for this matrix, okay? Because if there were other eigenvalues, I would have added some additional subspaces here, okay? But since there is no additional subspace here, I see that there is only one eigenvalue of this matrix, which is equal to 3, all right? So then what can I say about the characteristic polynomial of this matrix? The matrix is 8 by 8, and I have discovered that it has only a single eigenvalue, which is equal to 3. As a result, its characteristic polynomial should be s minus 3 to the power. The characteristic polynomial has always, in this case, with a single eigenvalue, we will always have this eigenvalue repeated 8 times. Okay, because the characteristic polynomial should have the general order equal to n, and n is equal to 8 for this matrix, so the summation of the powers in the characteristic polynomial should be 8. Since there is only a single power there is only a single distinct eigenvalue, its power should be 8. So here let us look at these null spaces. I have null space of, I'm defining here sigma 1, a minus 3 identity, and this is going to give me null space of sigma 1, and null space of sigma 1 square, and null space of sigma 1 cube. Okay? And this has dimension 8, this has dimension 7, and this has dimension 5. Okay? And now I'm wondering about the minimal polynomial. What happens if I increase the power of this matrix in this case? What is the dimension of null space of sigma 1 to the power 4? Will it be able to increase, will the dimension be able to increase any further? No, we have already reached the overall space dimension. What does that mean? That means that this sigma 1 cube is actually the zero matrix. Okay? So if a null space of a matrix has the dimension of the overall space, that means that any vector is inside any vector in the overall space is inside the null space of that matrix. And if any vector is inside the null space of that matrix should be equal to the zero matrix. So here, implicitly here, we know that sigma 1 cube matrix is 0, 8 by 8 by this fact that its null space is C8. Okay? So we see that this null space increase will not continue. I'm going to have an equal space at null space of sigma 1 to the power 4. Okay? And its dimension is going to be 8. So we see that we reach the largest null space at the power 3 here. Okay? At the power 3. And here we know that the power at which we reach the largest null space is the power mi, multiplicity of the eigenvalue in the minimal polynomial. Okay? That means that the minimal polynomial of this matrix should be s minus 3 to the power 3, because the largest null space is reached at the power 3 here with the dimension 8, which is the characteristic polynomial power. Okay? So now we have to find the Jordan canonical form. Before that, I can ask you the following question. How many linearly independent eigenvectors can this matrix have? What is the maximum number of linearly independent eigenvectors that this matrix can have? Okay? In that case, you need to look at the dimension of the null space of sigma 1. It is the eigenspace in that case, and the dimension of that null space, or the eigenspace, is going to give you the maximum number of linearly independent eigenvectors for the eigenvalue 3. Okay? But since 3 is the only distinct eigenvalue, this is going to be the maximum number of eigenvectors of this matrix. All right? So that number is going to be 5. So there can be at most 5 linearly independent eigenvectors for such a matrix, which would satisfy these properties. Now let us look at the Jordan canonical form. For Jordan canonical form, I'm going to look at these dimensions. All right? So the first thing that I'm going to look at is the dimension of null space of sigma 1. Okay? This dimension is 5, and I know that this is going to be the number of Jordan blocks for the eigenvalue 3. This is the number of Jordan blocks with size larger than or equal to 1, or just the number of Jordan blocks for lambda 1 equals to 3. And I have the only single eigenvalue, therefore this is going to be the total number of Jordan blocks. So the total number of Jordan blocks is 5 here. All right? And then I'm going to look at the consecutive differences here. Dimension of null space of sigma 1 square minus dimension of null space of sigma 1. This difference is 2 here, and that is going to be the number of Jordan blocks with size larger than or equal to 2 for lambda 1 equals to 3. Okay? So Jordan blocks with size larger than or equal to 2 is 2 for this matrix. And then I'm going to look at the next consecutive difference here. So dimension of null space of sigma 1 cube minus dimension of null space of sigma 1 square. This is going to be, the difference is 1 here. And therefore 1 is the number of Jordan blocks with size larger than or equal to 3 for lambda 1 equals to 3. Okay? Then the next consecutive difference will be equal to 0, because we have already reached the largest null space here. Let me write it as well. Null space of sigma 1 to the 4 minus null space of sigma 1 cube is 0. And this is the number of Jordan blocks with size larger than or equal to 4 for lambda 1 equals to 3. Okay? So now from these numbers I can actually try to extract the total number of blocks with different sizes. So we see that I have 0 Jordan blocks whose size is 4 or larger. Okay? And the number of Jordan blocks whose size is larger than or equal to 3 is 1. Okay? So therefore here, from this information, I get that the number of blocks whose size is equal to 3 is just 1. So let me write here, number of Jordan blocks with size equal to 3 is 1. Okay? Because of these two numbers, the difference is just 1. And what about the number of Jordan blocks with size equal to 2? In this case, I have 2 Jordan blocks whose size is larger than or equal to 2, and I have 1 Jordan block whose size is larger than or equal to 3. Okay? So when passing from here to here, the number is decreased by 1. That means that the number of Jordan blocks with size equal to 2 is just 1 as well. Okay? And what about the number of Jordan blocks with size equal to 1? 1 by 1 Jordan blocks. And that is going to be just this difference. Okay? So the total number of Jordan blocks is 5. And one of them has size 3, one of them has size 2. So therefore, and there are no Jordan blocks with size larger than or equal to 4. That means that the number of Jordan blocks whose size is 1 should be 5 minus 2 here. Okay? So that is going to be 3. All right? So we see that here, in this case, we have 1 3 by 3 block, 1 2 by 2 block, and 3 1 by 1 blocks. All right? So now let us try to draw the Jordan canonical form of this matrix. So the Jordan canonical form of this matrix is going to contain first a 3 by 3 block. When I try to obtain Jordan blocks, I always and in this course we would like you to always order the blocks from the largest to to the smallest ones. Okay? So, of course, if you change the order, that would be also a valid Jordan canonical form for the matrix, but we don't think that they are going to be, they are different than the first one. So, when we try to obtain the Jordan canonical form in this course, we will always order the blocks from the largest to the smallest ones. Okay? The other ones are also valid Jordan blocks, but we won't consider them. We will consider them to be the equivalent to the first one that we obtain here. So let us say I have a 3 by 3 block, which means that this is my first Jordan block, and then I have one 2 by 2 block, this one, and I have 3 1 by 1 blocks. This one, and this one here. Okay? So this is going to be the Jordan canonical form of a matrix which would satisfy that dimension criteria. Okay? And what is the size of the largest block? It is 3 by 3. You see that the minimal polynomial has the power 3. Okay? So this 3 is the size of the largest block, and you see that the total size is 8 by 8 here, just as the original matrix. All right? So if you get here some numbers, and at the end, if the size doesn't hold to be equal to the original size of the matrix, then that means that you made a mistake somewhere in the process. All right? So this completes this example, and I will solve one more here. Let me erase this one as well. So suppose that A is in C 4 by 4. So I have a 4 by 4 matrix, and I have a single eigenvalue. Lambda 1 is equal to 7. And suppose that in addition to this, I know that M1 is 2. Okay? Of course, there are infinitely many such matrices, and actually, such matrices might have more than one single type of Jordan form. So, of course, every matrix has a single Jordan canonical form, but here we are considering infinitely many different matrices, and some of those matrices, if I take 2 of those matrices, then they might have different Jordan canonical forms. Okay? So here the task is find all possible Jordan canonical forms such matrices can have. I'm repeating here, every matrix has a single Jordan canonical form. Okay? Of course, the block changes. Changing the order of the blocks does not count here. So every matrix has a single Jordan canonical form, but here there are infinitely many different matrices that might have different Jordan canonical forms from each other here with these specifications. So we are going to find what type of Jordan canonical forms does such matrices have. So here we are given the facts that we have a single eigenvalue and the minimal polynomial power for lambda 1 is 2. So I have here, what is the characteristic polynomial in this case? This is a 4 by 4 matrix. If it has a single eigenvalue, then its characteristic polynomial is going to have this form. Okay? And the minimal polynomial is also given to us because I know this power. I know that it is s minus 7 square. Okay? Now I'm going to ask the following question. What are the dimensions of these null spaces? Null space, so I will define what sigma 1 is first. A minus 7 identity. Okay? And I would have here null space of sigma 1. null space of sigma 1 square, and I will continue null space of sigma 1 cube, etc. Okay? And in order to be able to find the possible Jordan canonical forms such matrices can have, I need to know the dimensions of such null spaces. All right? So here, let us say that I don't know the relationships here. Okay? In this case, when do we reach the largest null space? At which power we are going to reach the largest null space? We know that that power is going to be the minimal polynomial power. So this null space of sigma 1 square is the largest null space that we can reach in this case. So this null space will not be able to grow anymore when I go to the power 3. And similarly, there should be a proper subset relationship here, because this really can't be the largest null space in this case, because otherwise the minimal polynomial power would have been equal to 1. Okay? So since the minimal polynomial power is 2, null space of sigma 1 square is the largest null space, and 2 is the first power that we reach the largest null space. Okay? And what is the dimension of that largest null space? We know that this should be, the dimension should be equal to Ri, the corresponding power of the eigenvalue in the characteristic polynomial. So this dimension is 4. And I know that any null space on the right of that one will be equal to 4. But I know that the dimension of this null space is going to be strictly smaller than this 4. Okay? And actually, I know that that dimension also will be larger than or equal to 1, because every eigenvalue should have at least one linearly independent eigenvector. That means that the dimension of this null space, this eigenspace, is always going to be larger than or equal to 1. And there should be a strictly smaller sign here, because there is a strict growth here from this null space to the other one. Therefore, what are the possibilities for the eigenspace dimension here? This dimension can be equal to 3, this dimension can be equal to 2, and this dimension can be equal to 1. Okay? Are there any other possibilities? It can't be equal to 4 or larger, and it can't be equal to 0 exactly. Okay? So we have these 3 possibilities, and that is what we are going to consider for the Jordan canonical forms here. Let us consider the first case. Case 1. Dimension of null space of sigma 1 is equal to 3. This is my first possibility, okay? And in that case, what about the dimensions? Sigma 1, null space of sigma 1 square. This is always 4, and this is 3 here. And I know that sigma 1 cube is again 4. All right? So now let us look at these number of Jordan blocks. So number of Jordan blocks is, in this case, 3, this dimension. Okay? And what about the number of Jordan blocks with size larger than or equal to 2? Okay? And here, 4 lambda 1 equals to 7. Okay? I am wondering about this number. And this number is going to be the difference in this case. Okay? And that is going to be 1. So one Jordan block whose size is larger than or equal to 2. What is the total number of, what is the number of Jordan blocks with size larger than or equal to 3? So number of Jordan blocks with size larger than or equal to 3 for lambda 1 is equal to 7. What is that number? It's going to be this consecutive difference, and that is going to be 0. All right? So now just from this information I can obtain the overall number of Jordan blocks for each size. So how many Jordan blocks whose size is larger than or equal to 3? So I have 0 Jordan blocks in that case. So what about the total number of Jordan blocks whose size is equal to 2? In that case, it is going to be just this difference, 1 minus 0. So there will be 1 Jordan block with size equal to 2. Okay? And how many Jordan blocks with size equal to 1? It is just going to be this difference. Okay? So I have 2 Jordan blocks with size equal to 1. Okay? So in this case, let us just try to obtain the Jordan canonical form. In this case, I have 1 Jordan block with size equal to 2. So I would have eigenvalues like this. And 2 Jordan blocks whose size is 1, 7. And I would have 7, even like this. So this is my first possible Jordan canonical form. Okay? Of course, I can here play with the orders of these blocks, but we are going to consider only this one. And we are going to consider all the other order changes to be equivalent to this one, where I ordered the blocks from the largest to the smallest one. Okay? And what about the other case? So this is my first case. Let us look at case 2. And in this case, I will assume dimension of null space of sigma 1 is 2. All right? So in this case, if I look at these null space dimensions, then it's going to be 4, 2, and 4 here. All right? Now let us try to obtain the overall Jordan block numbers. So I have number of Jordan blocks is this dimension, which is equal to 2. Number of Jordan blocks with size larger than or equal to 2 for the single eigenvalue 7, this is going to be equal to this difference, 2. And number of Jordan blocks with size larger than or equal to 3 is 0. It's going to be this consecutive difference. So we see here that I would have, so I have number of Jordan blocks whose with size equal to 2. This is going to be 2. I have 2 Jordan blocks with size exactly equal to 2. And how many Jordan blocks with size equal to 1? That is going to be just this difference, which is equal to 0. So only 2 Jordan blocks, and both of their sizes are 2. And that means that our Jordan canonical form would be looking like this. 7, 7, 1. This is my first 2 by 2 block. And the other one is just like this. Okay? So this is my second possibility. Let us now look at the third possibility, case 3. And in this case, we are assuming that the dimension of null space of sigma 1 is 1. All right? So if I look at these null space dimensions, as I have null space of sigma 1, null space of sigma 1 square, and I have equality null space of sigma 1 cube. These dimensions are 4 here, and this dimension is 1. Okay? So now let us look at this case. What is the total number of Jordan blocks? That is equal to 1, this dimension. And number of Jordan blocks with size larger than or equal to 2. In this case, this is going to be this consecutive difference, 3. And the number of Jordan blocks with size larger than or equal to 3 is this consecutive difference, which is 0. All right? So now, does everything make sense? When you look at these numbers, do you think everything is making sense here? The total number of Jordan blocks is 1, but the number of Jordan blocks with size larger than or equal to 2 is 3 here. It really doesn't make any sense here. How can I have a single Jordan block while I have 3 more Jordan blocks whose size is larger than or equal to 3? Larger than or equal to 2, sorry. So these numbers really do not make any sense. Okay? So here we see something important. These null space dimensions cannot really be arbitrary increasing numbers. They cannot be first increasing, arbitrary, first increasing and then remaining constant numbers. Okay? They have to satisfy some constraints. So you see that here, these consecutive differences, they should either get smaller, the consecutive differences, they should either get smaller or remain equal to each other. Okay? So, and in this case, we see the reverse. These consecutive differences are increasing. Such a possibility cannot happen in any matrix. Okay? So that this means that we cannot have such an A matrix. Okay? We cannot have such an A matrix. Okay? So really, we really do not have a case 3 here. We only have 2 cases which are possible, and the third case is actually impossible. So here, what do we see? Why is that impossible? You see that these numbers, these consecutive number of Jordan blocks with size, with the total number of Jordan blocks whose size is larger than or equal to 2, larger than or equal to 3, etc. These numbers should always be either decreasing or remaining constant. In the earlier examples, you see that this number decreased, and it remained constant. In this one, it remained constant and then it decreased. All right? So these consecutive differences, they should always either decrease or remain constant. If they are increasing, then such a possibility would not be okay for us. We won't have, for any matrix, we won't have the case where these consecutive differences would be strictly increasing. It really doesn't make any sense. So here, therefore, we can say that there is no such an A matrix which would satisfy these dimensions. That is why we really do not have to consider case 3 here. Okay? So we only have 2 possibilities, 2 Jordan canonical forms. The first one is in this form, and the second one is in this form. Okay? That completes this example. So now we have completed our investigation of finding the Jordan canonical form. Now we're going to look at how to find a P matrix that would put the matrix A into this Jordan canonical form. Okay? So now we are starting on the concept of how to find a P matrix, a basis change matrix, which satisfies Jordan canonical form is equal to P inverse AP. Okay? We are looking for a P matrix that would give our simplified representation for the matrix A, which is equal to the Jordan canonical form. Okay? And now our task is to find what P would be, or how we can find such a P matrix. Okay? So that is also going to come from the structures of these null spaces. Remember, these null spaces have dimension R1, R2, and Rk, and these subspaces are invariant subspaces. Okay? And if I try to find some basis sets for each of these null spaces, and then if I fill those basis sets into the columns of my P matrix, then I can try to obtain a P matrix which would give me a block diagonal representation. But we know that in the Jordan canonical form, each individual block is also very special. We really do not want blocks which are filled with non-zero elements. So we would really want the blocks to have some structure. We want eigenvalues on the main diagonal, and one above the main diagonal we should have either 0 or 1. And the rest of the block should be equal to 0. Okay? And therefore, by finding only some arbitrary basis sets to these null spaces, we won't be able to achieve our aim. In that case, J or A bar, which we called it before, will not be in the Jordan canonical form if I find an arbitrary basis for these null spaces. Okay? So we need to find some very, very specific basis sets for obtaining the simple representation in the Jordan canonical form. Okay? So now let us look at how we can try to obtain some basis sets for these null spaces. In order to be able to find those specific basis sets, again we are going to use this specific structure of these null spaces. Okay? So last time I have drawn this, but I'm going to be drawing it many times. You will get bored. So I would have null space of sigma I here, and this one gets larger, sigma I square, and this growth is going to continue until null space of sigma I to the mi minus 1, and the largest one is going to be null space of sigma I to the mi. Okay? So I have these null space structures like this. Okay? So then we have to find basis vectors or the basis sets for the largest null space here. You see that our invariant subspace is the largest one here we obtain. All right. So what is the dimension of the basis? What is the dimension of this largest space? Its dimension is Ri. Okay. And as a result, in the basis set of this largest null space, there needs to be Ri basis vectors. Okay, that is the meaning of the dimension. So I need to form a basis set, a very, very specific basis set, which is composed of Ri vectors to this largest null space. And I have to do it for all of the null spaces here. Okay? And then I need to put them into my P matrix, and if I choose my basis vectors in a very specific way, I would see that the simple representation that I obtain has the Jordan canonical form. Okay? So in order to be able to find these basis vectors, we are going to use the concept of chains. Let me write. We use the concept of chains to find the basis set for null space of sigma I to the mi. Okay? We form our basis sets, we form our chains as follows. The first thing we do is to select a vector x here. We find a vector x which is inside the largest null space, but which is not inside one inner null space. Okay? So we can always find x in null space of sigma I to the power mi, but x is not in null space of sigma I to the mi minus 1. Okay? Why can we always find such an x? Because from this null space to this null space, there is a strict growth. Okay? There is not an equality here, because this is my largest null space, and the other ones should be strictly smaller than this one. As a result, in this largest null space, there are always some vectors, some additional vectors, which are not inside the one smaller null space. Okay? So there are always some so this disk is never empty. Okay? So I can always find an x vector which is inside the largest null space, but which is not inside one strictly smaller null space. There always exists such an x. Okay? Then what do we do? After finding this x, we define the chain of vectors. This chain of vectors would be composed of as follows: sigma I to the mi minus 1x, sigma I to the mi minus 2x. These continue until sigma ix, and I would have an x. Okay? This is my chain of vectors. This is a single chain of vectors. All right? So now I'm wondering about the properties of this chain of vectors. Okay, how many vectors are there here? How many vectors are there in this chain of vectors? We see that this is my first vector, second vector, and mi my first, second, and I need to continue from the zeroth power of sigma I. X is just identity times x, and identity is sigma I to the power 0 times x, and then sigma I to the power 1x, and then I have sigma I to the power m minus 1x. Okay? So how many vectors are there here? Because of this zeroth power here, I need to have the integer powers from 0 to mi minus 1. As a result, I would in total have mi vectors here. Okay? So suppose that these vectors are linearly independent. Then do you think they can form a basis for this largest null space? If these vectors are all linearly independent, and if they are inside this largest null space, do you think this can be this single chain can be a basis set for this largest null space? The answer is it depends. So the dimension of the largest null space is Ri. Okay? So, and the number of vectors in the chain is mi. Okay? If mi is equal to Ri for a specific eigenvalue, then this chain of vectors can be a basis for this largest null space. But if Ri is strictly larger than the number of vectors here, then I would know that in any basis of this largest null space, I need to have Ri linearly independent vectors. Therefore, this single chain would not be sufficient in that case. Okay? So what am I going to do in that case? I would try to find additional chains here to complete the total number of vectors to Ri, which is the dimension of the largest null space. So when Ri is strictly larger than mi, we're going to see that we will need to find additional chain of vectors in order to be able to complete the total number of basis vectors to Ri, which is the dimension of the subspace I'm trying to find a basis for. All right? But here, now I have a single chain, and I would like to examine the properties of this single chain. Okay? So now let me ask you the following question. Can any element of this chain of vectors, can any element be equal to 0? Can any element in this chain of mi vectors be equal to 0? So here let us think. Can sigma I mi minus 1x be equal to 0? I know that x should not be inside the null space of sigma I to the power mi minus 1. I always find such an x which would satisfy the following condition. Okay? What about these two conditions? What do they mean? X in a null space of sigma I to the mi, this would mean that sigma I to the mi times x is equal to 0 vector. Okay? And X is not in null space of sigma I to the power mi minus 1 means that sigma I to the power mi minus 1 x should be non-zero. Okay? So if I find my x correctly, the first vector cannot be equal to 0. Okay? What about the second vector? Can this be equal to 0? If this is equal to 0, if I multiply it with sigma I, then sigma I to the mi minus 1 times x would again be equal to 0. Okay? So if this vector is equal to 0, then the other one should be equal to 0 as well. As a result, this vector cannot be equal to 0 either. So I'm repeating here, if this vector is equal to 0, then I can multiply this. Let me do it here. If sigma I to the mi minus 2x is equal to 0, then I can multiply both sides of this equation with sigma I. Okay? Then this would give me sigma I mi minus 1x is equal to 0. Okay? So you see that if this vector is equal to 0, the other one is going to turn out to be equal to 0, which is not possible because of this condition I chose x. Okay? So this can't be equal to 0. And you can see that none of the vectors here can be equal to 0. Okay? So that is an important fact here. If I can form such a chain of vectors by choosing x with these conditions, then none of the vectors here can be equal to 0 because of this condition. All right? What about linear independence? Are these vectors inside this chain, are they linearly independent, or some of them can be linearly dependent with each other? Let me try to investigate that. Okay? In order to investigate the linear independence question, I will look at a linear combination of these vectors and it will equate the linear combination to 0. And then I will check if the coefficients of that linear combination can be non-zero for some cases. So let me write here alpha 1 sigma I mi minus 1x plus alpha 2 sigma I mi minus 2x going until I would have here alpha mi minus 1 sigma I x plus alpha mi times x is equal to 0. I equate an arbitrary linear combination of these vectors inside this chain to 0. And if I can show that all of the coefficients here are equal to 0, then I know that these vectors should be linearly independent. On the other hand, if I can see that this equality can be satisfied for some non-zero coefficients, then these vectors will be linearly dependent here. Okay? But here we will see at the end that these vectors should be linearly independent, because I will be able to show, by starting with such an equation, I will be able to show that all of these coefficients are equal to 0. Okay? How can I show that these coefficients are all equal to 0? Or how can I show that these vectors should be all linearly independent? Here is how. I will multiply both sides of this equation by sigma I to the power mi minus 1. Okay? If I do that multiplication, I would have alpha 1 sigma I to the 2mi minus 2 x plus alpha 2 sigma I 2mi minus 3 going until alpha mi minus 1. So I would have sigma I mi x plus alpha mi sigma I mi minus 1 x is equal to 0. That matrix times 0 is still 0. Okay? Now let us look at these vectors. I have here sigma I mi x equals to 0. Okay? Why is that? Because x is inside sigma I to the mi null space. Okay? Therefore, sigma I to the mi x should be equal to 0. So this is 0. And all of the earlier vectors have higher power than mi on top of sigma I. Okay? All of the vectors on the left have higher powers than mi to the left. So they should be equal to 0 as well. Why? Because if sigma I x is equal to 0, then I can multiply here this equation with any power of sigma I, and I would get with any positive or 0 power of sigma I to obtain that sigma I to the power mi plus something times x is equal to 0. So all of the other vectors are 0 as well. Okay? So from here I get only this condition, alpha mi, sigma I to the mi minus 1 x is equal to 0. And I know that by the conditions of x, sigma I to the mi minus 1 x is non-zero. So this is not equal to 0. I have a non-zero vector times a coefficient which is equal to the 0 vector. So that means that this alpha mi should be equal to 0. Okay? So I have shown that the last coefficient of the first equation should be equal to 0. Okay? So now let me write that equation once again. Alpha 1, sigma I to the mi minus 1x plus alpha 2, sigma I mi minus 2x, going until alpha mi minus 1, sigma ix is equal to 0. Because the last coefficient should be equal to 0. Okay? So I have this equation. Now I have to apply the same idea here. Okay? In order to get the same idea, I can actually try to show that this last coefficient is again going to be equal to 0 if I multiply both sides of this equation with which matrix? I'm going to multiply both sides of this equation with the matrix sigma I to the, here in the last vector I want sigma I to the mi minus 1x. Okay? As a result, I will multiply both sides of this equation from the left by the matrix sigma I to the power mi minus 2. Okay? And that is going to give me alpha 1 sigma I 2mi minus 3x plus alpha 2 sigma I 2mi minus 4x going until alpha mi minus 2 mi minus 2 here times I have sigma I mix plus the last coefficient alpha mi minus 1 sigma I mi minus 1x is equal to 0. Okay? So I have this equation. Here I have written also the second term from the right here. Okay, it is going to be this term. This term here, one before this term, is going to be sigma I square x, and sigma I square x times this matrix is going to be sigma I to the power mix. Now I know that this is equal to 0, and all of the higher powered ones are equal to 0. Okay, and then I would get the last one only. mi minus 1 sigma I to the power mi minus 1x is equal to 0. I know that this is non-zero, which means that alpha mi minus 1 is equal to 0. So you see that I could actually show that the second coefficient from the last should be equal to 0 as well. So I could continue in this manner, okay, with the same logic over and over by decreasing the powers of these matrices that I multiply this equation with from the left. Okay? And then I can show that all of those coefficients are equal to 0. That is going to mean that these vectors inside this chain, they should always be linearly independent. Okay? I could continue this logic until the last coefficient to show that all coefficients are equal to 0, which means that the vectors in the chain are all linearly independent. Okay? So if I can obtain such an x, and if I form this chain of vectors, those vectors will be surely linearly independent. I really do not have to check whether they are linearly independent or not, because it is it can be theoretically shown that they are linearly independent. Okay? So now I'm going to look at where these vectors are lying in this structure. This is my null space structure, and I'm wondering where each of these vectors are lying in this structure. Okay? And I know already one of them, where one of them is lying. Which one is it? I know where X is. X is in this disk. Okay, it's inside this largest null space, but it's not in the one inner null space. Okay, so X is living in this disk here, in this outermost disk. So let me look at this first vector, sigma I mi minus 1x. Where is sigma I mi minus 1x? Okay. Where in this structure is this first vector? Let me try to find it. This vector is non-zero because sigma I to the mi minus 1x should be non-zero. But you see that sigma I mi times x is equal to 0. Okay? So if I multiply this vector from the left with the matrix sigma I, then the result should be equal to 0. Sigma I times sigma I mi minus 1x is equal to sigma I to the mix, and this should be equal to 0. Okay? So then what can you say about this first vector? This first vector, sigma I mi minus 1 times x, should be inside the null space of sigma I. Okay? But this is my eigenspace. Null space of sigma I is null space of A minus lambda I identity. And any vector, any non-zero vector in this null space would be an eigenvector. Okay? So that means that this sigma I mi minus 1, it is non-zero. I know that it is non-zero because of this property. And since it is inside this null space, x is an eigenvector. Okay? And where is it living in this structure? In the innermost disk, right? It is the innermost circle is our eigenspace. All right? So I have sigma I to the mi minus 1x living here in the eigenspace, and it's an eigenvector. Okay? So this vector is an eigenvector. So when I form a chain of vectors, the first vector of that chain is always an eigenvector. Let me write it. The first vector of the chain is an eigenvector. Okay? So we know this fact. What about the other vectors? We are going to see that none of them are actually eigenvectors. So none of the other vectors are going to be inside this innermost circle. Okay? None of the other vectors would be an eigenvector, but we will call them as generalized eigenvectors. The other vectors in the chain are not eigenvectors, but they are called generalized eigenvectors. So each chain, when we calculate such a chain, its first element is an eigenvector, and I have n minus 1 other elements here, and each of them are generalized eigenvectors. Okay? They are called generalized eigenvectors. And I still haven't answered where the other vectors are, or I still didn't answer the question of why the other vectors are not eigenvectors. Let us try to understand the other vectors. So I know that this x is in this outermost disk. What about sigma ix? Where is sigma ix, okay, in this structure, all right? And I have found the places of first and the last vectors, and I'm now wondering where the other vectors are in this structure, all right? So let me look at sigma ix. So I will ask you the following question. Can sigma ix be inside the outermost disk? Okay? So here we are wondering about if sigma ix is going to be inside null space of sigma I to the power mi, but it is not going to be inside sigma I to the mi minus 1. Okay? So here is what I'm going to do. I will multiply this sigma ix vector with the matrix sigma I to the mi minus 1. Okay? So what is that going to give me? This is going to be sigma I to the mi minus 1 plus 1 here, mix, but this is equal to 0 because of this property. Okay? So you see that this sigma ix is inside null space of sigma I to the mi minus 1. Okay? So you see that this sigma ix vector should be inside this not in the largest null space, but in the second largest null space. Okay? So sigma ix should be here. But can it be inside? Can it be, for example, inside sigma I to the mi minus 2x? I know that it is inside this ellipse here, but can it be inside in one inner ellipse? Okay? So I'm going to answer that question by the following. Can this vector, sigma ix, be inside null space of mi minus 2? Null space of sigma I to the power mi minus 2. What is this result? This is going to be sigma I to the mi minus 1x. There is a power mi minus 2 here, and there is the power 1 here. So this is sigma I to the power mi minus 1x. And can this be equal to 0? This can't be equal to 0 definitely because of the x property here. Okay? So this is non-zero. So what can I say about the sigma ix, the vector sigma ix then? Can sigma ix be inside null space of sigma I to the power mi minus 2? Can this vector be inside the null space of this matrix? No, the result cannot be 0. So this sigma ix is not in one inner null space. So we see that sigma ix is here in this disk, okay? Second outermost disk, all right? What about the other vectors? So if you take each of the vectors here one by one, you would see that these vectors, as I multiply x with sigma I over and over, these vectors would be traveling towards inside this null space structure. Okay? So I would have sigma ix here. In the next disk, I would have sigma I square x. In the next disk, I would have sigma I cube x, etc. Until I have sigma I to the power mi minus 1x as the eigenvector in the innermost disk. Okay? So here, in the one outer disk of the eigenspace, I would have sigma I to the mi minus 2x. Okay? Maybe I should put this here. So these vectors, as we multiply x with sigma I over and over, these vectors would be traveling towards inside this null space structure. Okay? And the first one would always be an eigenvector inside the eigenspace, and the other ones will never be inside this innermost ellipse, and they would be in the outer disks. Therefore, since the other vectors are not inside the innermost ellipse here, we know that they are not going to be eigenvectors, but they are going to be called generalized eigenvectors. Okay? And the other spaces are actually called generalized eigenspaces. So we have the actual eigenspace as the innermost ellipse here. The outer ellipses are here, not disks, the ellipses, the whole ellipse is called a generalized eigenspace. All right? So now we are going to see that when we form our basis vectors for these largest null spaces out of some chains, there might be multiple chains in order to be able to complete the basis set, number of basis set elements to the overall dimension. There will be multiple chains, and when we're going to see that when we form our basis sets for the largest null spaces out of these chains, the resulting simple representation, this P inverse AP, when we fill in those basis sets into our P matrices, and when we calculate the new representation A bar in this manner, that A bar is going to be in the Jordan canonical form. Okay? So therefore the concept of chain will be very important, and we are going to learn how to find such chains and how to use those chains in order to be able to obtain the basis sets for these null spaces in the coming lectures. So in the coming lectures we will learn how to choose these columns of this P matrix out of those chains, and then we will actually try to show that when we choose our P matrix out of such columns from the chains, we will see that our new representations will be in the Jordan canonical form. So A bar is going to turn out to be in Jordan canonical form. Okay? But these are for the coming lectures. That's all for this lecture. Thank you very much again for watching. Bye-bye.